So we are going to make sure that we can identify and describe key features of graphs. Now, many of these you may have seen in Algebra 1, but we need to make sure that you remember all about all of these features. So you're going to want to take notes in your foldable, and you're probably going to want to write small because we're going to squeeze a lot of information on this foldable. Okay, so I'm going to start with the blue line. So the blue line is linear. So that means that this is a linear. I would put all of your notes basically wherever I'm going to write them because I'm leaving space for other stuff. Linear. Linear. That is a linear function. Now remember, we know some things about linear functions. We know that we can find the rise over the run to find the slope. So if we find 2 points on this line, like I'll pick this point and this pretty point, I can say that the graph goes down 1 and over to the right. 1, 2, 3, 4. So that's to the right 4 and down 1. So that means that the slope of this graph, m, remember, equals the slope. And that equals -1 rise over +4 run. So the slope of that is -4. Some other key information. This point right here, remember that is called an x-intercept. The x-intercepts actually have lots of different names, but we'll just label that one as an x-intercept right now. That's about all we're going to say. This is obviously has a negative slope. So you might also hear people say it has a negative slope. Okay, that's all the information we're going to write about the linear function right now. Let's move on to the green one. So let's take a look at the green one. Let me make this writing a little bit smaller. So the green one, this is an absolute value function. I'm going to write that up here. This is an absolute value function. It's an absolute value function. We can see that it is decreasing as you come down this way. So I'm going to put decreasing. We always read graphs from left to right. So I'm basically starting over here and going down this way. So this is decreasing. It's a decreasing function. And then we hit the bottom here, and then it starts going uphill, right? So that means when it's going uphill, that is increasing. So this function is decreasing and then increasing. This bottom point right here, this green guy right here, is a vertex. So I'm going to put a little right out here. This guy here is a vertex. And he happens to be a minimum because he is a low value. Remember from Algebra 1, minimums are the valleys. Minimum. So that means that the vertex of this would be at the point -3, 2. And the minimum value, obviously, it has the height of 2. So the minimum of that has the height of 2. Okay, that's about all we're going to say about the absolute value function. Let's look at this red guy now. Okay, the red one is a cubic function. I'm going to write that way down here. Cubic function. It's a cubic function. Remember, we always read our graphs from left to right. So I'm going to actually write that in black over here because it pertains to all of them. So always read graphs from left to right. And that means you're going to start at the leftmost point, which happens to be here, and then you're going to be traveling up and then down and then up. So this red graph is going to be increasing. So increasing. And then we get up to the top right here. That point right there is called a relative max. This is a relative max. I'm going to write max. It's really a maximum, but we know we could just write max, a relative maximum there. And then when you travel around here, then the graph starts to decrease, right? And then it gets down to this bottom point here. That is a relative min or relative minimum. Relative minimum. And then we start coming back up, and then the graph starts increasing again. So graphs can be just like this linear right here. That is just straight up decreasing all the way. But this red cubic function is increasing, hits that relative max, and it has a turning point, comes back down, decreasing, has another turning point down here, relative min, and starts coming back up and increasing. This has actually 3 x-intercepts. It has a y-intercept right here hidden in this junk, but it has 3 x-intercepts. I'm going to draw those in purple. So you see it crosses, remember this is your x-axis right here. This is it crosses it right here, and right here, and right here. Obviously you should have some colored pencils or something. So these 3 dots, see the 3 purple? Has 3 zeros, or x-intercepts. Remember, those are called zeros from your Algebra 1, also known as x-intercepts. They're also known as solutions. And I'm going to put a little arrow to all 3 of them. That one, and that one, right? So we have 3 zeros or x-intercepts. And I think that's about all the information I'm going to go ahead and put on the first graph because it's getting kind of busy. You do see that we do have a y-intercept here. So we do have some more key features on here, but we just want to make sure we name some of them. So make sure you have some different colors. And make sure you named all of the items that we talked about. Let's go to the second picture. Okay, we got 3 graphs on this second picture. Let's see. Let's start with this bluish purplish one. Okay. So this bluish purplish one is an exponential function. It is exponential. Remember, those are the ones that look kind of like ramps. They're just kind of going, looks almost flat, even though it's not totally flat. It still is going uphill a little bit, even though you can't even tell. And then it just takes off exponentially. So that's an exponential function. So an exponential function has an asymptote. Let's see, this is right down here. Let me try to draw it in a different color. So do you see how this, I'm going to start drawing a dashed line right down here. Actually, you know, I could just use the dash, can't I? Should I use the dashed line? Okay, I'm going to make it really skinny though. Okay, so this dash line, okay, do you see it? It's green right now. So this is, I'm going to scoot it up a little bit because it really is up a little bit higher. Okay, so do you see the little green dashed line? So the little green dashed line, you notice this blue line comes down and see how it gets really, really close to this green line. It gets really, really close to it. It keeps getting closer and closer and closer. If you were to keep going forever, it would just get closer and closer and closer, but it would never, ever, ever touch. And so that means that this is the asymptote, which means that the graph is coming super duper close to it, but never actually touches it. It's kind of like a wall that's never ever going to cross and never ever going to touch. Just gets closer and closer and closer and closer and closer forever. Okay, so that is, this case is called a horizontal, because it's horizontal, obviously. A horizontal asymptote. So this is a horizontal ASYMPTOTE. Okay, that is a horizontal asymptote, and it actually is at this level right here, which is at y equals -2. That means the graph drops down and gets really, really close to where y is -2, this horizontal line. I'll label him y equals -2 over here too, so you can see. That's what that green dashed line is. So usually they'll put a little dashed line that tells you it gets really, really close to that. Okay, let's talk about some other things about this graph. Now this graph is going to keep going forever and ever this way, right? It's also going to keep getting higher and higher and higher and higher and scooting to the right. So we talk about end behavior. So let me write about end behavior. We'll learn more about this, but let's just introduce it. End behavior. Now, end behavior means as this graph moves further and further to the right. So as we move further and further to the right, so as x goes towards positive infinity, because infinity is this way, right? That's my infinity sign. Sorry, it's kind of ugly. As x moves towards positive infinity, the graph, which we call f of x, moves up high and into positive infinity, moves also towards positive infinity. So what this is saying, as x gets higher this way, so as we travel this way, this graph is just going to keep getting higher and higher and higher and higher and more to the right. So it's as x moves towards positive infinity this way, the graph moves towards positive infinity up towards the sky. So they're going to be both positive infinities. Let me erase this part right here. So that was just me traveling. And like I said, we're going to hit end behavior a lot more, but I just wanted to introduce it. Okay, let's look at the black graph. Okay, the black graph, this guy right here, is a square root function. Square root function. And what does it look like this graph is doing? It looks like it's doing the same thing. As it travels towards positive infinity, which is the right, it also travels up high to positive infinity. So the end behavior of this square root function is also, as x travels towards positive infinity, f of x also travels towards positive infinity, because it keeps getting higher and higher the more you go to the right, and it's going to keep going up. Let's go ahead. Let's label this. This is a y-intercept, just in case we have forgotten. That is a y-intercept. Make sure we label one of those so we have it in our notes. This function has no x-intercept. Okay, let's go hit the red one. Okay, the red one's got a lot of stuff going on. Okay, so I'm going to switch to red. All right, the red one is called a quadratic function. Quadratic. quadratic function. And remember, we also call that a parabola. Quadratic function, also known as a parabola. Now remember, these are U-shaped. They could be right side up or upside down. In this case, this is an upside down one. Remember right here, we do have a maximum vertex. So we do have a vertex up here, also known as a maximum because it is like a mountaintop. I'm going to abbreviate it max. So this graph, as you're traveling up, remember you always start with on the left-hand side. When you're coming up, this graph is increasing, correct? This is increasing on this side. It's increasing basically until we hit, see, increase. We're about to hit a turning point. So it's increasing until about -4, right? So it's increasing forever down here till -4. And then what happens when you get on this side of this vertex? Then it's going to start decreasing, right? So I'm going to write decreasing on this side. Okay, that says decreasing. Sorry about the hot mess there. Maybe I should make that a little bit nicer. Not very much nicer. Okay, so increasing, hits this turning point at my maximum vertex and then starts decreasing. Now, people might look at this graph and be like, oh no, it's decreasing on both sides. But that doesn't make sense because you always have to start on the left-hand side, and this is the left over here. So I'm always going to start here and think about that. If I was to just ride my bicycle up this is clearly increasing and then decreasing. So always travel from start on this side of the graph and get on the graph here. So this exponential function, if I get on it, you see how it's increasing. Remember, this is all increasing, even though it looks almost flat. It is increasing tiny bit, and then it's increasing a whole bunch. Same thing with this black one. If I get on it from this side, this graph is increasing forever, forever and ever. Okay, so there's some stuff about the let's talk about end behavior of this guy. So let's talk about end behavior of this red guy. So as this red guy moves to the right, which is as x goes to positive infinity is over here. So as x goes to positive infinity, which is this way, as x goes to positive infinity, what happens to the graph? You see what the graph is doing? The graph, f of x, is going down to negative infinity because negative infinity is down this way, right? It's going downhill. So as we move to the right, which is x getting positive, right? The graph itself goes downhill. So the graph goes towards negative infinity. Okay, let's talk about end behavior on this side. Now remember, end behavior is just the way the graph behaves at the end. That's why they call it end behavior. So what do you think the end behavior? Maybe I should label this end behavior. I'll just put N. So the end behavior on this side, what is it doing on this side? Okay, so as the graph is going this way, so which way is this way? It's going towards negative infinity. As the graph, as x moves towards negative infinity, so as this goes this way, what's happening to the graph? So as x goes to negative infinity, that means traveling on the x-axis this way. What's happening to the graph? As you're moving this way, the graph is going, so the graph is called the f of x, is going also down, which is negative infinity. So the end behavior of this parabola on the right-hand side, as my x values increase, as x goes to positive infinity, my graph goes downhill to negative infinity. If I look at the other end, as my x goes backwards to negative infinity, bloop, it also goes downhill. Now you might come at me and say, I thought you said we always travel from left to right. Now we do travel from left to right when we're talking about increasing and decreasing. But when we're talking about end behavior, we do travel from basically from the middle, because it's as x goes positive. See how it has x? So we want x values getting positive, and this one is as x goes negative. So for end behavior, we are starting basically, in my head, I think about starting at 0, 0. I'm going this way and that way. And which way does the graph go? And in this case, they both go, the graph goes down this way and down that way. So increasing and decreasing are different from end behavior. Okay, let's see what else we have here. We should talk about slope or rate of change. Now remember when we had linear functions. Remember when we had linear, we picked 2 pretty points on the graph and we did rise over run. So we went down 1 and ran 4, just like you did when you graphed like in 7th grade. Now we can do that with graphs that are curved also, but we then call it just an average rate of change. So I'm going to write in this little area right here because I have enough space. Now remember, if you don't have enough space, then just write over here and put a little arrow to it. So I'm going to go ahead, I'm going to do it in green so that way you could see it. So you can find an average rate of change in between any 2 random points. So like if I pick this is a nice pretty point on the graph, right? Oh, maybe I should go up here because then I have a little bit more space. So see how this is a nice pretty point because the graph crosses right at the X of the grid. And I have another nice pretty point right here. Okay, so I could find like the average rate of change in between those. So that is in between the interval of, see how I'm dropping right down to my x-axis? It is in between the interval of, what is that, -9 and -7. So, oopsie, that's supposed to be a bracket, a square bracket. Let me erase that. So bracket -9, comma, -7. Oh my gosh, seriously, I just did it again. Okay. Took me forever to do some practice. So in between this little area, I could find the average rate of change. So I can do my rise over run between these. So between these points, I have to rise 2 and run 2. So my average rate of change, I don't just say rate of change, I'm going to say average rate of change. Remember, rate of change is slope. Average rate of change is going to be 2 over 2, right? It's a positive, it's going uphill. 2 over 2 is equal to just 1. So my average rate of change between the interval of -9 and -7 is equal to just +1 because it was 2 over 2, which is 1. So you can find average rates of change, and it's going to be different depending on where you come on the graph, because here it was rise 2, run 2. But what if I did average rate of change from like here to here? So the interval from +3 to 5 is going to be a -4 over 2. So the slopes is going to change. So that's why we do average rates of change in certain intervals, because it depends on where you go. It's going to be different. Now, if you're on a linear is a constant rate of change, remember? And that means I could pick any 2 points anywhere, and they're going to simplify to -1/4, no matter what. See, look, if I pick like this pretty point here and this pretty point here, that's still going to be down 1 and over 4 because it's linear, it's constant rate of change. Okay, I think that's about all I'm going to put on here. Now, obviously, both of these graphs have a lot more stuff that we did not label. Like that was a y-intercept. We have another y-intercept here. We have x-intercepts here, also known as solutions. This parabola here, quadratic function, has two solutions. One right here at negative, I don't know, 13 point something. And we have one way over here at positive 5 point something. So these graphs do have more than what we have talked about, but make sure you have all of these labeled. Obviously, if we try to label every single feature of every single graph, we're going to run out of paper. So hopefully you can pause the video, make sure you color code stuff and point to stuff with arrows. And if you can't read my writing, I hope you're listening to the video because that's going to be easier to be able to read it. It's very hard to write on a screen. This is going to be glued into your notebook. Make sure you have all of these notes.